Thanks for reminding me. Are you recording it?
I can. I wasn't at that point, but
Cool.
oh,
Just to those of you who've just popped in, because I've just started recording, I'm explaining what finite element analysis is, and basically, doing structural analysis is a complicated thing, and finite element analysis takes a lot of the variables that go into it, and they calculate it all at once. Um, there are like we're talking here about something that could be as complicated as working out all the atoms reacting and molecules reacting to each other, but but we don't have computers powerful enough for that, and so instead we have these really abstract ways of approaching um, physics and engineering using Cartesian coordinates and uh, force diagrams to be able to solve these problems. So um, the critical, I guess, computational design slash mathematical thing that finite element analysis uses to do this well is a technique or a tool called graph theory. Um, it is basically the process of setting up nodes. So you can see here these nodes 1, 2, 3, 4, 5, 6, and creating connections between those nodes. And in complex systems, nodes can be connected unidirectionally, and could even not have connections. So in this case, I'm not sure what the double line there is referring to, but you can have nodes that connect in one direction and so on and so forth. And we can actually, this maths is quite famous for trying to solve the pathway, the bridge path, this one, the bridges of Königsberg. There's this little town in Germany with 7 bridges and 4 land masses, and it's connected in this way. And the town, there was always debate over whether or not and how you can go on a walk, just a single person going on a walk through Königsberg and crossing each bridge only once. And it can be solved with graph theory, which is effectively creating a node at each of these points and connections between them to be able to map that out. I can say now, graph theory is probably one of the least understood things in computational design that should be understood. Like, obviously, artificial intelligence and generative design, there's a lot of different things that we can use, but I believe graph theory is probably the most powerful one that we have at our disposal at the moment. Um, and very little people, I think, actually understand how to use it. It is the engine behind social media. Um, it's the reason why, like, are, are, are any of you here actually worried about what social media knows about you? Like, has any of you ever just quit Facebook for a month and just not put stuff in, but still you're still getting like advertising with it? Like, they still kind of know who you are, even though you're not necessarily telling them anything about yourself. Um, the thing is, like, if you actually think about it, if this particular map that we're looking at here is a friendship group connection rather than structural or walking through a town connection. If we just think about the network member A, they've got four friends. 1, 2, 3, 4. They're friends with E, B, C, and D. Now, A could be completely secretive about who they are and what they do, but E, D, C, and B could be completely active Facebook users, let's say, and basically Facebook can make assumptions about what you're interested in by the network connections that you've got with other people. So you're friends with a bunch of 30-year-olds. You might be friends with a 60-year-old, and they can make a fairly good assumption of how old you are and your gender and what you're interested in by the people that you're connected to. So that's where a lot of this stuff is being utilized to make really smart assumptions about, like, if you've got missing information in a system, then all of these networks help solve that. Does that not make sense to anyone? How about you, Alex? Perfect sense. Good. The idea, like the thing is, when we start looking at structures, we are actually looking at the perfect physical representation of a network, a graph theory diagram, where basically each point that you have a structural element joining with another element ends up becoming a node in a graph theory map, and the forces that can travel along these connections between each node are unidirectional. So you can have a gravitational force travel down this particular path. Am I sharing my screen? I think I am.
Yeah, we can see right now.
Excellent.
Yes.
No, all clear.
Pardon?
All clear.
All clear. Okay, thanks, Jack. Forces can travel down, and they can also travel up. And the nodes themselves then can also have properties, and the connections can have properties on them to be able to then allow the system to calculate. And in the back end of all of this, there's just a giant matrix. And when I say matrix, like if you end up seeing sort of these types of matrices, if you actually want to look in the back end, where various numbers in these systems are designed, they're placed in areas so that you can just take a big clump of matrices and subtract or dot product or multiply or add them together through that system, and the whole finite element analysis system solves what the solution is. So they, the result would be a certain deformation and so on and so forth. The thing is, and this is actually, it's such a simple rule that people just kind of miss, and I'm gonna have to repeat this to you guys quite a lot, I think. Hopefully not, but it's the thing that I've had to repeat to every student doing this, almost every student, is that the way that I've drawn this particular system might visually represent a graph, but it doesn't physically represent a graph, or as in, it doesn't represent the actual connection diagram of that graph. So the way that lines are drawn, I can draw, if I draw a line from start to finish, so from this point to that point, that line knows parametrically where its start point is and where its end point is. And that, in a way, is the means for these finite element analysis tools to know the connection that you're making. So by me putting, I'm going to do the social network example at the moment. So here's me. Here's Will. And I'm just going to pick some random person that in the class. We'll just go Sailor. I haven't spoken to Sailor directly yet. Sorry for honing in on you. It's just an example. If I draw a line from myself to Will to represent, a friendship or colleague connection there, the system knows it's effectively got a line that's connected snap bang on me and snap bang on Will to represent what's going on, and we can in a way say, rather than actually drawing this, the system's actually seeing whoop, it's huge. The system's seeing this. AB is connected to WH. And in some graph theory systems, you might actually represent this connection like so, where this particular pathway is the connection from myself to Will, and this particular pathway is the connection from Will to myself, which would then be written like that. So though AB connected to Will to WH is very different to WH connected to AB, but you could have systems that don't care about that, and that's what the structural ones don't. It assumes every single one of these is unidirectional. So that's why it usually draws a line, because we're actually just using a physical drawing of a design to represent this graph. The thing is, if I moved Will down, and I don't know why I had to move Will, and Sailor, I end up putting Sailor here. What does that diagram then mean visually?
You don't know Will, but you know Sailor.
Yeah, so visually it's saying I know Sailor, and Sailor is I'm friends with Sailor, and Sailor's friends with Will, right? That's kind of what it says visually.
So basically, the friend of your friend.
Yeah, but this line, if I actually turn on its control points, it's actually connecting me with Will, not Sailor. And so this diagram, topologically, it could be drawn like this. It can be drawn, it can be drawn like this, and it can also be drawn like this. The computer doesn't care. It only cares about which node is connected to which other node by the line that is drawn between. Right? So what ends up happening is, now if I transfer this now into more of a structural diagram, see this line that I've drawn? The line goes from this point to this point. So it's almost like saying, okay, we're going to connect this node, this kind of like connection of members at this point, and this connection of members with this beam. The system won't know that we're actually intending on the webs of this truss to actually be joined to this this member here, this cross beam, the flange, the bottom flange. It doesn't understand what's happening there, and so it needs to know that you want those connected by effectively having separate lines going from each node to each node. Okay? Does that make sense?
Yeah.
That is very different to this. Cool?
Andrew, can I ask?
Yes, go on.
So is it going to treat that bottom section as 3 individual things, or
Yeah.
has it just done that so it knows that it's connected?
Yes, it's going to treat them as 3 individual members. Because in a structural graph, they are 3 individual members.
Okay.
Okay?
So there's no way to make a 1 and still have them connecting.
No, but look, let's think about this for a moment. If I draw a single beam and I put a joint in the middle of it, and now that joint could be any type of joint. Let's make this a, I'll make this a support. So so I've got a beam, I put a joint there. Now, when we talk about the joints that we were dealing with, talking about last week and the week before, we've got rigid joints and pin joints, right? Those are 2 of the more common joints that we can see. We also see movement joints and various other ones, but the more common ones are rigid and pin. Now, if I made that joint a pin joint, what would we see? What would happen to this structure?
The upper side just falling down.
Yeah, exactly. Yeah, this guy here cantilevering out, it would fall down. But if I made this a rigid joint, we'd see this go into bending, right? It'd probably do something like this. Yep. So the idea is, normally, when we're working with systems like simple finite element analysis tools like Karamba, is that these rigid joints that we set in those systems are so rigid, they're so well crafted that we can treat them as if they're a continual connection from one beam to another. So that beam ends up just becoming a single object. So in this case, if we went through and we made the connection between these 3 objects a rigid connection, and we made these pin connections with this beam, then the result would be that this would actually act as a single beam, because those rigid joints would transfer the energy the same way that having a single beam running through there would work.
Yeah, that's what I was worried about. So if you make those pin joints, they'll act as 3 different things. But if you're making them rigid joints, it's going to act as 1, just with 2 joints in the side.
Yep. And I guess if you've got the same, because so I've just sort of got touched on the subject that these particular connections, and Karamba doesn't actually work this way, but we'll get into that in a moment. Those connections are connections that can have properties on them. So we can basically say whether or not they are rigid or pinned, or we can actually also control the axis of freedom of movement. So if you think about your elbow can't necessarily, specifically your elbow can't it can torsion in a way, and it can also rotate in one axis, but it can't rotate in the other. It's your shoulder that ends up doing that. So you can limit the freedom of movement with these things as well. So we are sort of touching on ideas of BIM here. Like you've been using Revit for 4 weeks now, or 3. like, have you guys got an understanding of what BIM actually is inferring? Like, what? This is a good. Does anyone have a good definition of what BIM is, and don't just chuck it into Google and read it out? What does BIM stand for? Have you been taught that?
Building information modeling.
Right, and what does that infer?
It's creating an accurate model of a building that you want to build or is built.
Right, but what's one of the really important things? Like, we don't always model. Models usually infer, geometry. But what's the I stand for in BIM?
Information.
So what's the other thing that's getting modeled digitally?
There's,
The information, right?
yeah.
So that's the type of theory that we're tapping into here, is that there's information associated with each of these joints, and there's information also associated with each of these members for the final system to be able to calculate properly. So we're not just drawing geometry in this system now, we are also needing to produce a second parallel layer of information for each of these objects to be able to describe how that object works in the system. And for typical uses of BIM with Revit is that information normally helps you draw a better, well, not better, but a section faster, or a plan faster, or it lets someone audit or schedule outdoors better. You would hope. Doesn't always work that way. But that underlying information is important for the computer to be able to understand and help with that system. And so we've got to do that when we make these models. So are we at a point now where everyone has Karumba installed? Can you put up your hand if you don't have it installed? Excellent. Okay, I'm going to assume that means everyone's got it. So you should be able to find it in Grasshopper here, and we are going to do the most simple thing first, and then we will upgrade and try to do something a little bit more complicated. So the most simple thing that we can do is a bridge that looks like this diagrammatically. So a pin jointed bridge spanning from one support to another. I'm going to... You guys don't need to draw this diagram. What I need you to do is draw a line. We need to cover a few things before we do that, though. Karumba is an engineering tool, and so the system wants to use engineers' units. So typically, I will open up a Rhino model, and I will set that Rhino model to be in millimeters as I open it. Or if I open up a Revit model, that Revit model is going to be in millimeters when you pick the international units option for that one. But if you remember back to literally the first tutorial, engineers, they're working in meters when they work in international standard. So Karumba is also going to work in meters, and it's which is a little bit contradictory because there are some parts of it that don't want to work in meters, but we'll talk about them in a moment. But the main engine works in meters. So if we're doing any modeling with it, we need to make sure that it is at least the Rhino model is in meters, and our Grasshopper model is working in meters. Otherwise, you will have to do a bunch of scaling. And look, when you're troubleshooting these things in the future, and everything just kind of looks like it's going nuts, and the everything's tiny, it's probably that you're working in the wrong scale. So just keep that as a note. So I've just quickly drawn what is it's a 1/2 meter beam. Let's make this a little bit longer. Let's make this a 5 meter beam. And I'm currently drawing in plan view. I need to rotate that so that gravity is down for my beam. So there's my beam. And all we really care about is that line. So you just need to draw a line, basically. But I'll just use, we can use these supports just as an example for me. Okay, so we have a line. If we look at Karumba, Karumba is designed in a way where you have to basically design a model and assign properties to it, and then you put that model into an engine to calculate it, and then that engine spits out a solution model, and there's a bunch of tools that allow you to then analyze that solution model. So first, we've got to build our model. The engine, you can find the one that we would use. We will be using this term is just the standard Analyze Karumba 3D system, and we are going to be using tools like line to beam to build our structural system. So this takes lines and it converts those lines into beams. So here we can see out of the element section, this is like a string that actually represents all the information that Karumba wants to use to solve that particular element. And if I actually duplicate that member, there's going to be, that's right. It doesn't like duplicates. That is a poor example. There we go. So, if we put more than one beam in, then there's a string representing each of those things. You can see there are a few other inputs that you can change. You can change its color, which I believe is new. Were you able to change its color before, Will?
I can't remember.
I don't think you were able to do that.
Yeah, maybe. I think that will just change how it renders at the end.
I haven't used this for 2 years, so
Yeah.
then there's ID. Now this is a useful thing later on when if we want to apply like typologies to beams. So just keep this one in mind, and then cross section. So that is just the profile that we were talking about. We're going to use just the default cross section that Karumba applies, and we'll just see what it does. And we'll talk about cross sections and how to change them in a minute. If I just plug that in, this thing's going to complain. It's not going to work. Whoops. We've got to build a model. It's going to complain for multiple reasons. We've got to build a model. How do we assemble model? Okay, so you create elements, you put those elements into a model, you then analyze that model, and now we're getting the right error. Model cannot be calculated, there are no supports. Okay, so if you just think about reality, what have I told Karumba? I've told Karumba there's a line spanning from this point in space to this one, and that's it. I've kind of told it it's cross-sectioned by default. Is there anything, just based on that warning, is there anything that you think that we've forgotten to do?
points at either.
adding
Oh no.
support.
Yeah, the points at either end. So the thing is, this thing does actually do points at either end. You know that it calculates these points and it says, okay, these are the points that make up that. These are the individual unique nodes in the system. But we need to be able to define support. So was it Declan? Did you say supports?
No, it was someone else. I said points.
Okay, this is all good. Someone said supports, and you're right. So, you know, the warning literally says there's no supports. So what I've done is I've drawn a beam, I've put it in space, you know, kind of in the atmosphere somewhere, and I've just said calculate. And the system says, this is so complicated. I'm not designed to work out how far the beam will fall when it's not supported. I must have a point of support. I need at least one point of support, and if that point is a pin joint, or a pin support, sorry, then you're going to need more than one, or otherwise the thing's just going to flop about. So it wants your building, your structure, to be sensible. So you can see here in the assemble model section, there is a support input. So if we go now look into Karumba, you know, we just have a bit of a snoop around. Here in model, we can see support. This is one of the most complicated, like Karumba makes some of the most complicated Grasshopper components. They change. They've got little user interfaces built into them. Like you can choose different things, and the component itself will change its inputs based on what you've chosen. So just be mindful if you're looking at someone else's script and you're wondering why you can't work out why yours looks different to theirs. It might be that the user interface that's built in has changed. So here we've got a support. We can pick supports by position or index. And and if I put both my points in, so that's all the points coming from my line to beam model, so that's just the start and end. Boop, boop. Sorry. And I I'm good. And I plug these supports into our model. We start to see the model itself is no longer giving us that no support error. It's still giving us an error. It's just this error is a more complicated one. And the reason I'm going through this and showing you the errors is that you guys are going to see these errors, and I need you to sort of understand what they mean as we hit them. And look, we're trying to do the most simple thing, which is placing a beam from one point to another, and we've already kind of hit like a whole bunch of errors. So just be mindful. This is going to be a fickle process, which is going to throw errors at you all the time. Now, the error that this is telling me is there are 6 rigid body modes in this system. This means some part can move freely without causing deformation. Try to use the eigenmodes component and activate the display of local coordinate axes. The first eigenmode will be the rigid body motion. If this does not help, check whether you have pinned support directly attached to a hinge. A hinge introduces an extra node, which may cause the problem. When analyzing a flat shell structure, one has to lock the rotation perpendicular to the plate and at least one node. Very, very complicated error, which doesn't really help a beginner. If you see this error whilst you're working on this particular set of assignments, then what that means for you is that you shouldn't use eigenmodes. Eigenmodes is like a special calculation mode for what we call funicular structures. These are structures that are flexible and allow more movement than what we would normally see in a rigid system. They basically it means that you can't use the same finite element analysis calculation methods that the simple ones that we're trying to use here. So eigenmodes run slower. What this means is that we've made a structure that is too floppy for the system to work out. In this case, it is because I've effectively, even though I've placed this support in, see these conditioners down here, Tx, Ty, Tz, Rx, Ry, Rz. These are the various different restrictions that they've allowed us to place on the supports to actually make them supports. So T stands for translation. So that means, you know, if I have these off, then the translation is unlocked. So these points in the system are allowed to move freely in the X direction, in the Y direction, and they're also allowed to move freely in the Z direction. And R stands for rotation. So they're allowed to rotate in the X-axis, in the Y-axis, and in the Z-axis. So this, with all of these off, it's almost like we don't have supports at all. And if I just lock the translation, so translation almost meaning like rollers or movement joints, if I lock these, actually if I just lock everything,
yeah, it needs at least one rotation.
Yeah, it needs one. If I lock everything, what we've effectively done is we've made a rigid joint structure. So this particular system is actually referring to a structure. I'm actually going to draw this in Grasshopper rather than Rhino. This particular system is referring to a support that looks like this, rather than this system. Let's do, we want it in the Y plane. This system, which would be referring to a pin joint, versus this system, will allow it to move in the X direction. Does that make sense? So they're you know, these simple diagrams that we've drawn for rigid pins and pin roller joints, support, sorry, we have a lot more control over that by effectively defining the axis of movements with this support system. So if I, you know, want to actually draw what I've drawn here, then we want to use this support to help model our system. Have I lost anyone? Okay, something that's really useful right now is the Karamba model view, which you can see in results. If you turn on, there's a component called model view. You plug your model into that. In Rhino, it will show you so here you can see these particular circles are showing you the axes that are locked. So the purple so it can't rotate like so, and it can't rotate like so, but it can rotate on this axis, right? Which is kind of what this triangular pin joint's almost inferring by its design, and it's not allowed to move in any of these directions. If I quickly just turn off one of these So that's a move in Y. You can see that locking symbol turns off. Cool. And then the one good thing that not one good thing, but one of the things that Crumba at least does is it assumes that you're on Earth. So you don't have to set that up by default. And it also assumes that the profile that any profiles that you do have on this thing are, they have weight, and so you don't have to set them as loads. So if we just had a simple beam that goes from point A to point B, then this is enough for us to get that going. So the model view is showing us it's showing us the actual, what's the word, the mathematical model. If you want, you can see a more complicated, realistic view of what you've actually modeled by going into the beam view. You guys can't see this. Beam view. By the way, they've designed this so that you can string components together, so you can have the assemble model be connected to the beam view, for example, and then the beam view connected to analyze, and then analyze connected to model view, and then model view connected to another beam view. Like this model lets you just string all of these things together and place these things where you need them. So you could, technically put your model view prior to your analyze, then run the model through the analysis, and then once the analysis is done, plug that into the beam view. And with beam view, please do what good. Okay, with beam view, it's now giving me a mesh representation of what we've modeled, and so you can see there's a pipe there that's describing the beam that goes from that point to that point. Cool? Now, if we insert in between the analyze and the beam, am I doing this right?
What are you looking for, Andrew?
No, we do need the model view, sorry.
Yeah, I think you should generally put analyze first. And then
Oh yeah, you if you use the model view first, it's purely, if you want to check the model prior to it breaking the analyze tool, for example. The model tool does let you play around with these types of settings, where if I now plug that into the beam view, does this actually have gravity? It should.
you need to put a gravity load in.
Do you?
So, yep, to go load, and then there's
Okay.
a gravity option.
Okay, I am wrong. So Karumba does not assume you're on Earth. It doesn't know that there's gravity. You have to tell that there is gravity. So there is this load. There is this load section. So you can find them in loads. Loads has almost all the loads that you care about. So one of them needs to be the gravity load. You basically don't need to plug anything into it. It knows everything it needs to. It's using -1 as a unit of Earth's gravitational force. If you chuck that into the load input, there we go. Then we are going to see, by sliding up and down the deformation slider, we're seeing our beam move into a deformed state. Now this is an extreme deformation. We are effectively timesing that the actual real deformation by 100 at the moment here to be able to actually see what's happening. So we usually, if we're going to be looking at any form of deformed model right now, we want to accentuate the deformation to be able to work out what's going on. And look, this right now we're looking at two pin joints. We can actually see, very quickly right now, if we made these pin joints rigid supports by just changing that rotational factor here. So this isn't allowed to rotate, and by making these rigid supports on either end, we're seeing a much better deformation result because of that support running through that. Do you guys can kind of see the benefits of being able to just quickly play with that?
My beam isn't deforming.
Okay, so this is the critical thing. I want to get everyone to this point. Everyone needs to have their beam deforming. So, Max, can you share your screen, so that we can work out what's going wrong, and hopefully other people can see if they've got the same problem as yourself. Okay, so Max, do you have a load applied to your model?
Yeah, I think so.
Yes, you do. I think your beam might be deforming. Can we just check?
I think it might be the scale.
Yeah, can we just check the scale?
Also, you're using the analyze component twice. It shouldn't matter, but I think you plugged it at the same time.
Oh.
Yeah,
I don't think that should make a
it
difference.
shouldn't make a difference. Can we just up the scale of the deformation? It does. Can you change it to be a pin joint rather than a rigid one? I think it's just a really small gap.
Just like that one there?
Yeah. Can you turn that off and on? No, turn on. It looks like you've drawn it in the Y direction. Turn on the X. Yeah, X axis.
There you go.
Yeah, you can see it move
Yeah,
slightly.
there's a tiny one there.
I think it's just tiny. How long is your line?
So how long is this line?
It's 2 meters.
Are you sure?
I think so. It's
Can you measure?
yeah, 2 meters.
Okay, cool. Yeah, it's just a really small deformation. Look, if you how do you do it? If you double click the little node of the 100 or of the slider.
Yep.
Double click the actual the node, that little circle.
Yep.
That then lets you control the minimum and maximum. So if you set that to like 1,000, there you can see that deforming more. So you do have a deforming beam. Good job.
I think it's just a case of a beam that thick isn't going to really deform
Yeah,
it.
it's
2 meter
not-
span.
No, not under its own weight. It's not.
Why was yours deforming so much then?
Mine's 5 meters.
Oh, I thought yours was 1 meter. Okay. So if I want to increase the beam size, is it just a matter of just changing the length of the line?
If you want to change the beam length,
Yeah, the beam length, sorry.
then yes, you can just change the length of your line. I've frozen I've locked myself into window death. There's a shit. There's a you can see this slider control. Can I do that? Okay, good. Shit, you can't see my screen anyway. Does anyone else not have a deforming beam?
My beam falls down so far that I can't see how far it falls.
Okay, look, can you share yours? Because guys, this is everyone's going to see these problems, and you've got to set up like the perfect situation. Oh, okay. Okay, so you have a deforming beam. Your beam is just deforming a crazy amount.
I think
Yeah.
you're using millimeter.
What is the length of your beam?
It's 500 mils.
Okay, so just to remember back to what I said earlier, this system is going to use meters. And it doesn't matter if you're drawing in millimeters.
Oh, is it interpreting? Oh, yeah.
It doesn't matter if you're drawing in millimeters or inches or anything. It's going to look at any unit that you draw and assume that it's a meter. So you've drawn a 500 meter beam, not a 500 millimeter beam. So number one, can you change your units to meters just so that you don't...
Okay.
So do you guys know how to change your units?
Isn't it?
Excellent.
Units.
You're going to show everyone how to do it, even
Yes.
if they don't know. Excellent. And when you do that, it's going to ask you to scale it. If you've already done a big drawing and you've been using millimeters, then go ahead and scale. But otherwise, just hit no.
Okay.
So now,
Okay,
how
now
long is
my-
your beam?
Oh,
You can just type length with the line selected if you want. 31
31
meters.
meters.
Still,
Cool.
look, seriously, it's very rare for us to have a beam, a single beam, going 31 meters.
Yeah.
And that's why you can see, you know, if you set your deformation to 1, you know, close to it, it's good
Yeah.
enough. You can see how much like you wouldn't normally expect to see steel looking like that, right?
No.
But
it's just
that's what it would look like if we actually
Right.
made a steel beam that size. It would deform very similar to that. So
Okay.
this is actually a really useful tool. You know, we wouldn't use Karumba in the real world to work out deformation. But you know, we have to assume all of our structures are going to deform. And so, you know, typically on a building like a bridge or a stadium roof, for example, the architects will design what they want the roof to look like, where the roof needs to be once the building's complete. And then engineers will take that model and reverse engineer what the structure should look like when it's fabricated, so that when it is put in place and all the weight of the structure is applied to it, it deforms into the position of what the architect has designed. And that's usually really only done when we know the deformation is going to be so big. So, you know, typically you do that on large spanning structures like convention roofs, stadium roofs, and bridges and stuff like that. So, does anyone else have something that looks abnormal? Either it's not working or it's going nuts.
I'll stop sharing.
I've got a grasshopper with Karumba.
Yeah, go on. No, yeah, we just
I'll start my video though because I'm doing it on a separate computer.
Okay, it's gonna be hard. Oh yeah, okay. Are you talking about those? Are you talking about those blood streams coming out of your panels?
Yeah.
Okay, I'll explain what that is. Okay, so this has nothing to do with Karumba. Grasshopper's obviously using like the Windows.NET framework to run itself. Every program on Windows normally does this, and almost every computer system and framework has a way of defining objects, like as in it has a way of defining what an integer is, it has a way of defining what a float is, it has a way of defining what a string is. So you guys have dealt with that in Python quite a lot. All of these systems have a limit though; they're not infinite. And so, like for example, integers versus doubles. Oh no, sorry, floats versus doubles are different. They're actually structured differently. They're a little bit. You've probably never heard of a double, but usually, mostly what we use in Python and Grasshopper, whenever we're using a number with a decimal point, we're actually using a double rather than a float. Floats, it's just the difference between a 64-bit object type versus a 32-bit. And it basically means you can have more precision in that number. So here you can see a float is allowed to only have, I believe, 1, 2, 3, 4, 5, 6, 7, 8 8 digits in its whole number, whilst a double is allowed to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 digits. And so doubles are more accurate. And that is because we are trying to store this information in a single 64-bit piece of information in that computer. And if we actually made a 128-bit number, then, and every number had to then be written that way, then we might be slowing down the system when we don't need that much accuracy. Now that same rule, for the number of digits for a float or a double, applies to strings as well. So what that particular panel is telling you is that Grasshopper can't render the string that you're asking the panel to represent, because it's got too many characters in it for that string to be able to do its job. Does that make sense?
Yeah, sort of. Yeah.
So are you
Sort of.
are you plugging strings into that,
I just have the
or
curve.
text curve? Just so you've plugged a curve in and it's broken.
Well, it doesn't even work if I like put it in from the start.
Hang on, I'm just
Well,
pinning your
I can
video
use
because
it.
Will keeps popping up instead of you.
I
You
can
just
use the function?
can you
but,
just delete the bloody delete them? I see these a lot, by the way. So if you just bring one in from scratch, what does it look like?
like that.
So it's still getting the blood red thing.
Yeah.
Maybe restart your Rhino.
Okay. Alright.
That's
Give that a try.
yeah, not like it shouldn't be breaking immediately. So then there's something wrong.
Okay. Alright.
Anyone
Yeah,
else?
I'll try that.
Anyone else without a deformation beam? Okay, excellent. So we're going to take this to the next level, and there is a whole magnitude of stuff that needs to happen for that to work. And the first thing I need you to do is I need you guys to either go grab your Warren Trust script from last week, or you're gonna have to start it from scratch if you didn't save it. Okay, so I'm gonna do mine from scratch because it's bloody easy.
Do you want to share your screen, Andrew?
Yes, I will share my screen. If we get enough time today, I think. Do you guys want to try do this stuff in Revit as well? Or is it maybe it's a bit much? What do you think, Will? It's maybe a bit much.
Let's just see where we get to. See what timing and where we get up to.
Yeah, I'm a bit. Yeah, I don't. Actually, I think this is probably. Yeah, that's me being very optimistic. Actually.
Yeah. It's also not just the timing. There's a lot taken in this lesson.
Yeah, there is. There is. Okay. Now I'm gonna make a shit version of my Warren Trust script. Actually, no, I'm not. I'm gonna make a good one. We will talk through the problems in a moment. Actually, this is the first time I've kind of taught Karumba this way, and I think it's probably the better way, right? Where it's as you teach it, you just basically create each of the problems so that everyone can see every problem. Do you know what I mean?
Yep, and it's slowly adding some more features.
Yeah. Because before, what we've done in the past is we've just basically gone, okay, this is how you do a perfect script, and then people run into problems and we let them try and work them out and we help them. I think it's probably better that we just show you all the common problems. I guess, is everyone done? Who will have a problem if I start on the next part right now? It shouldn't shouldn't have taken you long to do the Warren Truss. I guess if you here's my version of it. We're good? Okay. This bottom flange is a polyline. So it's made up of several lines. So it's a line that goes from this point to this point, so on and so on and so forth, which is the right way of drawing this line. If we could also draw this line like so, as in from the start to the finish. Like if I just pick out 0 and -1. And for this particular model, that will not be good. Because we want this model to understand that these members are joining this bottom flange. So we need to make sure that this line is made up of those separate lines. Just reiterating that. So, but the problem is, if I plug a single polyline into our system, hello? Who's that? Who is that? It sounds like Jack. Jack, we can hear you talking.
Not me.
Oh, okay, sounds like you.
Ooh.
Was it Will watching a video?
Not me. I'm on
Okay.
mute.
Okay, whatever. So, if we plug this particular line in, and maybe rather, what I'll do is I'll show this one, the zigzag one, zigzag. If I plug zigzags in, then what can we see at the end? What is the beam view showing us? You know, I've got literally like a zigzagged line running through, but what do we get as the beam view at the end? Can you see? Ravinder, do you mind muting? Or you can answer my question maybe. We've got this zigzag line, set of lines, but the end beam looks like the one from before, right? The beam goes from the start to the finish.
It's because it's looking at it from above or something, and it's seen it as one line or something.
Yes, you're right. You're correct. It's looking at it as one line.
I don't know why, but it is.
Okay, the reason why is because it doesn't care what the line is, how the line looks. It doesn't care if the line's got kinks or anything like that. What it's doing is it's looking at where the line starts and where the line ends, and it assumes that there is a straight line between the start and the end. Okay? So in this case, this is a single polyline curve, and we are telling it, you know, that it starts at this point and ends at that point, and therefore it doesn't care about any of these extra joints in here. We have to make sure that if we want those joints, those members to be understood as members, they all have to be individual objects in our system. So we have to explode them all. We have to explode them and make sure that they then connect for that now to work. Is everyone getting zigzags? The web? I should use technical terminology. Now what can we see? what has happened to my structure? Can you guys see what's? If I just go back to this previous model, see these guys here. What do they represent?
Support?
Right, and then Tim, just stay online. How many supports have I got?
11?
Right, and how many supports should I have?
2.
Right, so what have I done? Do you remember how I built the supports before?
Yep, you build using the line.
Yeah, so I took all the lines,
Yep.
I chucked them into the line to beam.
You use the point of the line
I got
to
the points.
build support.
So all of these nodes have now turned into supports. So what I've effectively done is I've got a hand of God coming in and holding all the structure up, right?
Yep.
And this is something that I've seen in so many people's designs coming out of this class, is their structure looks like it works fine. Then I open up their script and literally every single member in their structure is just being held up by these like random supports that just shouldn't be there.
Yep.
So this is the thing. We need to be really careful about how we generate our supports. And generally what I find is important is if you place a point in the model, we should be using these points as our support points rather than like picking points out of our model. And I'm going to get into why this is going to be a problem in a moment. So these 2 points, if I chuck them in now, look, we're going to start seeing that deformation happening on those zigzags, because now there's only supports on the ends rather than at every point in that truss. Now, I'm going to do something that might affect, it might actually be the case with some of you already. I'm going to take this point here that I've drawn, I'm going to move it over here. What are we getting? We're getting an error. The error is saying solution exception could not find node at, and then it gives us a position in space where the support number is 0, so that's index 0 of the support. So if I put a display on these supports, then that one's 0 and that one's 1, right? Let's make this smaller. So it's pretty simple. Basically, if that point isn't at the point at a node in anywhere in that structure, then the system won't understand that. It doesn't really understand what's going on. The point is in a completely different place. And so what is best to solve that is you do use these points. But what we do is we use a closest point relationship. So these are our supports, and these are our closest points. And rather than using the actual point itself, you can use the index. So this is index 0, and this is index 10. Actually, it's probably better. You are better off using the points. Sorry, don't use the index. Use the points. The reason is that we're going to be using more of these than, so we should be using the points. So if you plug those points in now, what will happen is, as these points move around, even though they're not necessarily at the exact position that they need to be, and the reason I say this is that you might have put a point there in your model, and from a distance it looks like it's perfect, but at an accurate level it's not, and the system doesn't know that. It has a threshold for its accuracy. Its accuracy has to be pretty spot on. By using the closest point system, you can make sure that your manually driven points are snapping to the points in your model, and those then work as supports. Does everyone have that working? Does everyone have manually controlled points in Rhino that then control the points snapping in Grasshopper. It's pretty straightforward. I think all of you should have used closest point by now, right?
Yep.
Yep, it's just guaranteeing that you're using the right point. Okay. So we can just chuck everything in to... Actually, I really like this process because it's literally showing us every problem that happens in Crumba. We can grab all our polylines and just throw them into this explode. And does it look like we've got a working model?
Nope.
Why?
The triangles are not connected to the beam on the top and the bottom.
Right. So, what do you think? What do you think's happening? What do you think is causing this problem? What is it? Let's have a look. Look, these triangles are deforming. Everything's deforming. The top beam's deforming, the bottom beam's deforming, but look, the top beam has a deformation where the supports are going from the top left to the right, but we've made a system that was meant to only support at this position and this position. So just have a look at my Grasshopper script. I'm gonna show you the state prior, and now just watch as I add this other polyline. What's changing?
It's adding the top and the bottom individually as separate.
Yeah, but
Line?
watch my script. Look at the difference. What's changing? Can you see?
Oh, the line changing the dollar line. So there's
Right. Do you guys know anything about what this dot dash line means?
multiple
you've
stream
made a
of
tree?
information.
Sorry, Tim. Just hold on. Who
Yep.
said the other thing?
You've made a tree.
Yep, Max. That is a whole can of worms. What you just said. Every set of data in Grasshopper is a tree. Okay, even this is a tree. Oops. Right, like a no data thing is a tree, technically. But you're right. What I think, just to read into what you just said, we've made a complicated set of branches, right?
Yeah.
Yep. So what that's doing, what all of this is doing is it's the same rules that apply to Grasshopper normally in every other situation, is that the branches are going to act individually. So you can work on multiple Karumba models at the same time if you run them all through different branches. So the branches that are coming out of these elements and the branches that are coming out of these points that are then making branches of supports and then are getting calculated in individual branches through this assemble model, through branches in the analyze, and so on and so forth. It is making a perfectly clean model for Karumba to analyze, but Karumba has no idea that these elements are in a system relative to this bottom element or the top element. And so, and the same applies, like with our closest point, we're doing that with branches and all of that. So in this particular case, it is actually appropriate to flatten the explode as it comes out, so that we are making sure that the structural model that we've drawn is being understood as a single element structural model. And it's very rare in this particular course that you are going to have to analyze multiple structural models at the same time. But just be aware that it is there, and the way to do it, in a clever, robust way, is by using branches. But let's just flatten this out, and we end up getting now a working truss with a fairly decent deformation, especially like my deformation was set to 100, right? So my 5 meter long truss now is barely deforming.
I think I've lost you a bit here.
Yep.
I had to remake the truss because the one we did in Grasshopper last week was in thousands of millimeters.
Yep.
It didn't work. It's
Yep.
like 55,000 meters here.
Yep, so
Um,
all you've got to do is change the length of the line, and it should work, right?
Yeah. But mine's working when it's not grafted. It's working as the branches.
Okay. You mean it's not working when it's flattened?
Yeah, sorry, it's not working when it's flattened. It's only working when it's grafted.
Okay, please share your screen. Let's have a look.
Well, I think I don't know what's happening.
No, let's dissect the problem, because it looks like it's working. Oh, that's because
If I found it, seems to remove the middle ones.
what? Do it again. What do you mean by remove?
Well, not remove. It's just not. I don't know. I don't know what's happened to the middle ones.
Are you
Is that meant
talking
to be-
about they're turning white?
Yeah, is that meant to be happening?
Yes. Don't worry
Okay.
about that.
Okay.
The you're currently looking at the bending.
The stress.
Yeah. So hang on. You know, you've turned on the axial stress, so you can see. If you look at mine, like I've just turned on my axial stress. So in the beam view, there's axial stress there that you can turn off and on. Like you can see cross section, you can see axial stress, you can see utilization or displacement, for example. With your axial stress, what you were just showing was red. I believe is showing compression, and blue is showing tension, and white is showing a balance. So what you were just doing was showing that you've got in that structure elements that were in basically a equilibrium of force.
Okay.
By it turning white, it wasn't removing it from the system.
And what did you do at the closest point? Because I think I've set my supports as like every point
Right.
instead of just those other two.
So what I've done is I'm getting all the points coming out of my line to beam method, and I'm using those as the cloud of points to look within. I've got 2 points drawn in Rhino, and you could make that any number of points. And I've drawn them so that they're relatively close to where I want my supports to be, and the closest point is then picking up the point in the model to be able to then use that in the support component. Does that make sense?
Yeah. Thank you.
Does anyone else have an abnormal looking truss? Especially, a good thing to do right now is to go into that deformation and just, jack it up. There we go. It's deforming very slightly. It might be worth me, doing this. Making this whole truss a lot longer just to get it to deform a bit more.
And we can also look at how you change cross section, which would
Yes, we will talk about that
impact
in a
deformation.
second. Yeah,
Sure.
we're layering up the complexities.
Andrew,
Yeah.
I don't know why it's not taking the top and bottom beam. It's not picking it up.
Okay. Do you wanna?
Oh, wait. I know why. Never
Okay.
mind. Did you just, for the top and bottom beams, did you just plumb in the same thing? Oh, you explode. Okay.
I
Never mind.
exploded them all in the one thing. Now look, this is going to change in a moment, because what we're going to do is we're going to actually start changing the profiles, all of this, because for the top the top flange and the bottom flange, we usually want a different profile, and structures aren't always the same profile. There's going to be different sizing throughout them. So I need to show you guys how to do that. So generally what happens is the stuff that happens prior to the assemble model is going to become a lot more complicated. And so you generally also probably want to go through and flatten your elements, your supports, and your loads. The one reason why we kind of want to flatten the system through here is because it is also going to be affecting our closest point. So if we've got any branches that are happening, branching before this closest point system, we probably want to get rid of them as well. So flattening that cloud will be useful in a moment. So we've got a truss, and Will was literally getting on to the next point, but we can control its size, its height, its length, the number of divisions, all of that type of stuff. But what we can't do is control currently its profile. We're using a circular hollow section steel. It looks like it's, roughly 500 in dimensions, so it's like pretty fucking big, actually. 500 CHS. No wonder it wasn't deforming in half a meter. And we want to be able to make this a bit more efficient because look, if I actually start looking at the axial stress through this thing, or maybe its utilization is probably a better example. We're barely using this structure. I'll get into what utilization you're kind of looking for at the moment, but the 3% is like it's tiny amount of utilization for a structure like this. If I look at its actual deformation of 1, then
And do you also want to plug that into the actual legend component so you can see those numbers with their colors and where they correspond to?
Sure, why not?
I just think that's something nice to have in the script.
I think, I find it can be quite confusing for some people. I was gonna lead into it, but we can definitely do it. So in the display tab, under graphs, there is a legend component. The way the guys have made Karumba is they've written it with this legend C and T value that just plugs directly into the C and T inputs of that legend component. So if you plug C and T and then drag this dude out, then it gives you like a colored legend of what we're seeing in Rhino. And it has the corresponding colors. So this bright red is being utilized at negative 3.5%. So that's 3.5% compression, and we've got only 1.6% of the structure being utilized in tension. And it's not 1.6 of the structure, it's like 1.6 of its actual structural integrity. So, we've got this giant beam that's got a certain amount of stress and strain, and we're only using, 1.6% of the capability of that member. Does that make sense? Or in this case, yours will be different. Okay, so we're going to see these numbers changing, hopefully, when we start playing around with these profiles. So, the blanket method, let's just say we're going to be using only one member for the whole structure. We can basically plug into the cross-section input a new cross-section. So, so how do we build a new cross-section? We just got to go find Karumba again. In the cross-sections area, there is the cross-section component. This is a component that has quite a lot of options to pick from. And it is in here that you can build eye sections, rectangular, so these are rectangular hollow sections, circular hollow sections, and then the other ones that you probably, is this actually going to let me, is this all there is? Trapezoid, spring, yeah, that's right.
I think that's the list. Trapezoid's the other one.
Yeah, trapezoid. What we care about is the rectangles, the circles, and the trapezoids. These other ones are more so designed for things like shell structures where the beam is actually the structure is actually a three-dimensional mesh. So we're going to just tap into the O section, seeing as that's kind of what we've got at the moment, or the circular hollow section. You can see here we've got diameter and thickness. And so if we go and grab a 500 being in millimeters, and we plug that in to diameter, then we're gonna, and we plug this thing into the cross section into the model, we're gonna see a change. Now, what do you guys predict will happen?
It'll get weaker.
Okay.
And I think it's gonna get massive because you've got your units wrong.
Thanks, Will. Thanks. That's what I was asking. That's what I was trying to ask. So what unit did I just use?
You use centimeters when you need to use meters.
No, I used millimeters. Normally, I think in millimeters. When I type 500, I mean millimeters.
Oh no, I meant like it literally says centimeters.
I know, you're right, Declan. You've delved deep into the component. Yep. So I think in millimeters normally. This is written by a German engineering firm, and they think in centimeters when they talk about their profiles. Actually, Germany's got a weird relationship with like the center leader and the centimeter and stuff like that. Like, for example, if you've ever been to Germany, they have like 50 cl bottles rather than 500 ml bottles and stuff like that. So just be mindful that whenever we're using any of these cross-section dimensions, we're actually needing to write them in centimeters. Actually, that's why you can see it's popped up there, diameter centimeters. So what I usually do, because I like still working in mils, I will just divide this by, is it 100? 10. So it's 50. What did you say? Who had a guess that it was going to get weaker?
That was me.
I reckon it's not going to change. Oh, it got bigger. Is it because my division's wrong?
Yeah, no. Yes.
50.
No, it should be right.
That's right. It's just that they were maybe 50 mil pipes, not 50. 500. 50 mil pipes? Yeah. So if we'll end up making this, I'll make this 100 mil. 50. There we go. Now, my deformation is set to 1. If I just set it to a lot higher, like 1,000. Ooh. And we start, increasing and decreasing the members, you guys can start seeing the effect on the structure, right?
I'm actually not getting any deformation.
Okay. Can you share your screen so we can see what's going on? Your deformation is turned off. There's a little tick box. There you go.
I didn't realize there was a tick box.
It doesn't look. It looks like your beam display is also in the wrong position. Maybe. Can you zoom out? See your See the beam on the. You've got a beam thing on the right. Far right. That guy. That go 2 to the right. That is your beam display. You've got that plugged into the analysis. What you want to do is plug that into your model display. So No. The one, that one. Yeah,
Okay.
that's going to show
There we
you
go.
deformation.
Right. I
Cool.
was wondering why this wasn't. Okay. Yeah. Okay.
You jack the deformation up to like 4,000.
Well, it wasn't doing anything.
I know,
so
it's good.
It was like, anyway. Okay. All right. Cool.
So yeah, look, there's going to be a lot of weird, fickle problems with this, and sometimes you just have to take a step back and look at the whole script. This is one of those situations where I think you guys need to share your problems with each other, because there's just so many different variables in play here that can cause this trouble. So if you've got a problem, when you share it, if you share it with me or Will, don't do it privately, do it in that main Slack section so that everyone can see that problem and see what the result would be of us trying to work it out. Okay?
Hey, Andrew.
Yeah.
There's nothing showing up on my legend.
Okay. Can you share your screen, please?
Yep.
Okay. The reason is that you've chosen cross section in your render settings. So in the beam view component,
Yep.
you have render settings at the bottom. At the moment, you're only showing the cross section. If you show that legend will change as you change from axial stress to utilization to displacement and so on.
Okay.
So that legend is corresponding to the information that you're rendering.
All right.
Cool.
Thanks.
No worries. Are we all good? So look, we're seeing we're actually seeing that when we are setting this thing to deform, as it gets thinner and thinner, what's actually happening is, the overall structure isn't deforming. The truss is actually keeping the thing slightly rigid, and what we end up seeing is that the members deform from node to node, because these are rigid nodes, right? And so those rigid.
You might want to start sharing again.
Sorry, my bad.
Sorry.
All good. So these rigid nodes, as I decrease and increase this thing, these rigid nodes end up becoming like the one thing that's actually just like structurally sound. So it's actually quite hard for us to define the strength of the rigidity of the node. It's assumed to be just absolutely like invincible in terms of its strength. And so you will see, when things get very thin, you'll see the rest of your structure failing before any of your rigid nodes or rigid supports fail. Especially rigid supports will never fail, basically. Cool? Now, I just want you to be really careful with these hollow sections. They also have a thickness. What I've seen in the past is people are effectively sometimes making like nuclear bomb bunker structures with their circular hollow sections, or rectangular hollow sections, or they end up putting a radius, a diameter in, and then the thickness of their structure of the inside ends up just being the full. It just fills up that whole thing with steel, and it's not good. So what you'll see here is if I throw that, there's diameter and there's thickness. If I throw a thickness into my cross section that is more than half the diameter, then it's going to break. Obviously, it says wall thickness is larger than half of diameter. A full circle will be generated, may cause errors. So basically, it's filling that whole thing up. It's making it solid steel, and it's not a hollow section. This is how you build rods in this system. So if you want to build like a thin cable that goes from point A to point B, cables aren't, or rod, they're not hollow, so you can fill them in. Otherwise, as long as that number is less than half, you're going to have a hollow section. Just please go look at various different circular hollow section sizes. So blue scope steel CHS sizes is a really useful thing to type into Google. There are, yes?
And yes, so we can also show there's actually like a cross-section selection list in Karumba if you want to go through after this.
Yeah, those are the European ones though. But yes.
It's good. It's got an Australian list.
Does
as
it?
well.
Oh, excellent. Excellent. That's not steel guide. If we go through here, this PDF, medium heavy and extra heavy pipes. I'm going to assume pipe is referring to CHS. Here it's telling us, you can see the outside diameter in millimeters, and you can see the only wall thicknesses available, okay, for that particular diameter. Because these are hot formed steel members, there is a device that extrudes them, and it is an incredibly hot and expensive process if you want to change how that works. So just quickly, so they heat the steel up. It's generally in this sort of like fairly pipe-like form anyway. Are they going to reform it? And then what they do is they've got a giant structural mold, extrusion mold, that this is then pressured through, and that hot steel is then formed. I hope they show the other side. As it's pushed through, it's forced into the shape of that mold. And so what I need you guys to do is you have to assume that you cannot, there you go, there it is coming out the other side, and then that effectively becomes the beam that you buy off the shelf. You have to assume you can't change these dimensions. It's just way too expensive to change any of these dimensions with this type of product. Okay? If someone says that your only option is 76.1 mil or 88.9 with one of these wall thicknesses, that's it. You can't make it any way, other way. And so one thing that I didn't necessarily enforce on the class in previous years, and I think has kind of failed, and I'm going to really make sure that you guys are doing this. If you are using any steel, like steel structure for the rest of this class that is using rectangular hollow sections, I-beams, U-beams, channels, anything like that, you need to go find the real dimensions of that thing and use that rather than coming up with your own, because I'm sick of, and this is not me talking to you guys directly, but I'm sick of seeing the structures sort of looking like this, where there's a pinhole of a hollow, circular hollow section, when in fact it should be more like, you know, that. And look at look at the effect on that deformation. Like, we're using 5 mils of wall thickness versus 50, and my deformation was set to like 1,000 times. It's almost nothing. but some people have been using. You can use your profile to change the how your structure works, and it's one of the variables you can't really play with. Now, how do you not get stuck into that? Even though you can control this manually. By the way, you can get into the rectangular hollow sections. You can get into the I-beams. I don't want to get too deep into that one today, but there's a whole bunch there. Let's go back to the hollow sections. This is a really big beam, but whatever. Will mentioned earlier that there are tables. Is it
It's the cross range selector.
Cross range. This one?
Sorry, yeah, the first one.
So with this component, we can filter through it and select Australian cross sections. We can tell it to give us either I-beams, circular hollow sections, or rectangular hollow sections. These rectangular ones also include squares. So we could pick the circular, and then just ignore family. This gets a little bit complicated, but there is a list that comes out of this with all those different members in the string setup the same way that Karamba wants. Now I believe there's another fancy component that they've written.
Yeah, the one below it.
This one.
Then you can enter in a name of something and it would get it, I think. Probably the best thing to do is set these particular max heights and widths. So, if you've got here we go. By reducing the dimension there, it's not really good, is it? How would you pick it? There must be a better component for this. Usually I use this one. I normally find that this is a bit too annoying for people, but here we go. Let's try this. Cross section selector. That just picks one. So yes, this one you either give it an index, which is the same as list item, or you can type a name. So I think if you type in 26, potentially it would find the first one that's got 26 in it.
But 26 could also be an index.
True. Yeah. You might end up putting more into it. 26.9. Not sure.
Okay. Look, rather than doing that, I'll just show you how to read this particular information for a moment. If you look here, you can see family, name, country, blah blah blah. The family and the name is probably the critical thing. And it's in the name. The name is made up of the diameter of the member, and then the width of the wall. So here, if we just scroll down, you can see if we want to get something, let's say 100, 150-ish, there's 165 diameter CHS here, and there's two wall thicknesses, 3 mil and 3.5. So let's go with the 3.5. We can pick out the 3.5. So that's index 47, and maybe later we can get into more complicated means of picking these out. So if I plug that in, that's now using the real dimensions that have been set by that table. And I'll just use a slider just to make that go up and down, just so that you guys can see the change. Ooh, how many do we have? 73. Ah, they actually changed in size.
Do you recommend we don't fiddle with it ourselves? Just grab one from this table.
Look, it's useful. You are going to have to fiddle with this manually, in a very short amount of time, like very very soon, because there is no table for balsa wood or pasta. Okay. So you will have to build something manually a little bit, because
So we are actually saying the strength to the material we used. We're not making like an extra bridge out of it. We're going for pasta strength.
More so, you know, we're gonna convert this to real world dimensions, because this thing doesn't really work that well to the dimensions that you've made. So we're gonna scale everything up, but we do want to make this, like, we want to use solid timber basically. And so there's no solid timber table. We're gonna have to build use solid timber is gonna have to be built with these trapezoids. So look, if you know, if I just quickly, without explaining too much, if I make a trapezoid and I change the upper width, the lower width, and the height, and I plug that in. This is currently solid steel. So I can change the widths. You know, this is looking more like my balsa structure. And then, whoop. And then in material, you can see there's a material selection component. It's got a whole bunch of materials in it. In here, there is a timber. So you can select, under select wood. We'll just pick wood, that's fine. And then plugging that in. This is now behaving like a realistically sized wood structure that we can use as an analog for pasta and balsa wood. Okay. But we'll get into what we're doing with these assignments, with this next assignment soon. I've just got to get through a little bit more of this. Okay, so we can control what these structural elements are made of, as in what their profiles are, and we can control the material in a way too. The thing is, we want to be able to control the members, the top members and the bottom members will want to be a different profile to the ones running through the center through the web. The flanges should be probably different members to the webs. So the way I think is easiest to do this is that your model needs to be broken up into separate components to be able to deal with this. So rather than having components going into a single element, we can have them go into two separate ones. So this guy here is going to be the flanges, and this guy is going to be the webs. And the way that we can tell Karumba to deal with that and put like a marker on it that makes it easier to manage later on is by naming them. So if we grab a panel, and you can name these anything, these are completely extensible names. We can name this flange on the top, and you put that in the ID. And you can name these webs. And these elements now need to plug in and merge as they go into the assemble model. And as well, we'll probably also need to do that with the points for the supports and so on and so forth. In doing so, what we've done is we've assigned some IDs to this so that when we are running these cross sections, we can actually assign these same names to the cross section. So we can say this particular cross section here is going to be flanges, and this cross section is going to be the webs. Oops. Make sure that's flat. So now that the web is plugged into this, as I slide this, up and down, we're only controlling the profile for the webs of this truss, or as I slide this one up and down, we're only controlling the flanges.
Can you just zoom out a bit?
Yeah.
What you just did?
So I've separated, just to re-clarify, I've separated the flanges into their own line to beam component and put a name into the ID. I've done the same for webs, so they're in there separate ones. They're plugging directly into the assemble model component, and then I've assigned flange and web to these cross section ranges. You can also assign that to this cross section here through this element ID thing, and this is effectively the BIM thing coming through. So we've assigned the ID so the model knows it needs to apply that profile based on the ID that we've set. Does that make sense to everybody? Has everyone got a model that allows them to control? Who doesn't have a model that allows them to control different profiles? We've got one more hour. We'll get.
What's a realistic level of deformation? Like, I just put in 4,000, but what does that actually represent?
It represents 4,000 times the deformation of reality. So, let's say it's moving 4 meters.
Yeah.
In reality, it's only going to move 4 millimeters. 1 millimeter.
Right. Okay.
Yeah?
Yeah.
And look, a 1 millimeter deformation on a steel structure like this is fine, The problem is, though, right now we're only telling it that there is it's only needing to support itself, right?
Yep.
But we'll get into loads in a second. Okay. Now, one thing that we want to change before we get into the complicated world of loads and whatnot is just the last thing that you can do. Is it the last thing? I guess so. It's the last thing that you can do to modify your structure. So at the moment, we are able to change whether or not our supports at either end are pin. So if I can make these rigid instead by turning these off and on. But all of the joints within our structure, they're all acting as if they're rigid. You guys can kind of make that out, right? If I end up making these members really thin, you can see all of the structure is acting as if it's a rigid joints. But we need to be able to tell Karumba whether or not these joints are pin joints or rigid joints. Now, Karumba doesn't do this via the joint itself. It does it by defining whether or not the member has a bending moment or not. And it sounds really complicated, But basically what we're saying is, like this diagonal, for example, if we're going to make this diagonal a pin joint on one end, we're basically going to have to make it a pin joint on the other as well. We have to basically turn all of our... If we want to make a member not have a... If I want a member to be a pin joint, we have to turn it effectively into a cable, which is... cables don't have bending moments. So the way that we do that is with this component that lets you edit the member. So in model, there is a component called...
Is it modify?
It might be modifier. No. Is it
I don't-
modifier? No.
No, I've got it on mine. It's called modify element, I think, which is go down. It's kind of halfway
Yeah,
down.
that one.
Yeah.
So we can modify elements. This thing gets really... This thing lets you do quite a lot. Okay? It lets you do a lot of different things. It lets you change its geometry. It lets you play with its buckling, all of that type of stuff. We don't want to mess with this too much. The only thing we want to do, and we're going to do this on our webs, and you're going to... Actually, we'll do this on everything, but first let's just do it on the webs. We plug our element into the beam component. There's a bending element. There's a bending input here. If you put a Boolean toggle into that, or any Boolean value, if you're making a complicated script, we can play with that as a true and false. So at the moment we'll set it to true, so it does nothing. If we replace that element and now we turn the bending moment off and on, we can see two things happening to our model. And I just want you guys to I'm going to take this off and I'll put this up. What's one of the major things that we're seeing change in the model? What can you see? Anyone? Come on, there's a blatantly obvious...
The web straightens or the flanges?
The web
inside ones they straighten.
The web straighten. That's a really good thing to notice. Okay, anything else? Is there a new symbol appearing?
Yeah, there's the orange things, yeah.
Yeah, so these orange rings are representing the pin joints. That's how Karumba is representing that. If these are distracting you, you can turn off the model view, and they won't be shown. Or as well, in the model view, you can actually turn on and off things through here. Like you can change its size. Where's its scale? Is it this one? No. Joints. There we go. The joint scale. So that one, you can shrink them if they're getting a bit too big. But I just want to get back to what you guys mentioned before. The webs ended up straightening. Now, why do you think they straightened? What else can you see? See this guy? What color is that? Or that one is that one's red and that one's blue.
Red and blue, yeah.
Right, there's solid red, solid blue. But look at this guy. It's got like bits of it that are white and bits of it that are red, and there's a little bit up here that's blue. And if I turn the bending on, what can we see now? It's not solid blue. There's a strong blue here, and there's a lighter blue on this other side, right? So by us turning off the bending the bending moment on those elements, we're actually also turning off the fact that that element can bend, right? So therefore they go straight. They can't be anything other than straight. They will not bend. And that is because we are inferring that if they have pin joints on either side, that those pin joints allow that element to rotate rather than bend to be able to apply forces. So we've now got an element running through here that is purely in tension, and an element that is purely in compression. Am I right? Yeah, yes. So this one's in compression, tension, equilibrium. Then compression, tension. You guys can see that? So, just another thing that I've noticed in previously is that people will design structures that have cables running through them. The cables don't have bending moments on them. I mean, they do. So they've modeled it so that it has a bending moment, which means, you know, this you have this thin thing, and I'm going to pretend as if this circular hollow section is a cable now. Okay, so let's assume that these are cables, even though they're hollow. You can see this cable is in tension, right? And this cable's in compression. Can you put a cable in compression? What does a cable immediately do once you put it in compression?
Slack.
Yeah, it doesn't work. So what that means is you actually need to remove this member from your model for it to actually work properly. It doesn't. The Karamba isn't clever enough to know that you need to remove that. Now there are better finite element analysis tools out there. You know, ones that actually cost money. That will, but in this case we have to do our own logic. So this member here needs to be removed if we are actually planning on making this truss just out of cables, because it's not going to support the structure. Cool.
Can you just go back to your Grasshopper view?
Yep.
Of when you split the thing to the flange and the web. What was the shift list or split list you were using to the right?
I just didn't, like, I've got different polylines and I've just put the polylines into a different component.
No, but when you went to the cross section, you used the list item.
Yeah. I'm just using these to pick that member.
Okay.
Yep. And now look, this whole thing changes. Look, you can start playing with actually what happens to this structure. You know, we can actually start experimenting and using a system like this to, as long as the model is built properly, actually investigate what is a better solution. So, you know, we could actually turn all of these elements into pin joints, you know, so they can all be rigid or they can all be pin, and we can start seeing, you know, if I now go over to the utilization, we've got 7% and 6%. If I make these pin joints, rigid, then the structure's ending up using almost double. We're actually, the structure's far less efficient with all of these being rigid versus all of these being pin. You can see 6.1, 7.1 versus 9, not double, but 50% worse. Do you guys see that? Mind you, I am doing this with a fairly unrealistic structure. So let's just size that up a bit. Okay? Cool. Now, we very rarely have structures that only need to support themselves. So how do we actually put weight on this? And it works very similarly to the way the supports work. This load component, it has the ability to change the type of load, and some of the, I find, easiest ways to do this is with the point load. Maybe in a few weeks' time we can talk about different types of loads when we in Karumba when we move on to the next assignment. With the point load, you basically pick you have to define a vector for the force applied, and that force is written in kilonewtons. So, let's just chuck a 1 kilonewton force downwards. And we can ignore moment, local, all of those types of things, except for position index. We've basically got to pick somewhere on our structure, and that somewhere needs to be a point in our structure for us to be able to put that load. And, just getting back to the support system, picking a point, defining a point somehow by defining it in Grasshopper or in Rhino, and then using the closest point system is probably the safest way of doing this so that it won't break the script. And using that point as a position, plugging that into load, and at the moment we're applying a load at this point here. If I slide that point along, you can see the points are deforming. The structure is deforming based on that 1 kilonewton node. Now, what have I drawn? I've drawn a truss that's 14 meters wide, long. That's 14 meters is quite a long way. So let's assume it's a road bridge. Can anyone have a stab at how many kilonewtons a regular car might be? Anyone?
8,000.
8,000. 8,000 what? Kilonewtons?
Yeah.
Is that just taking a stab, or is that a calculated guess?
No, that's actually just a guess.
Okay, no, that's a bit high. Okay, look, just seeing as you took a stab here, I'll let you work it through. So I just went and quickly grabbed car. I just typed car weight into Google. 1,524 kilograms. Do you remember a rough formula that we can use to convert that to newtons? What was it? X times, it's the weight, it's the mass of the object times what? I'm asking you, Kieran. Sorry. But
Oh, that's right. Yeah, it's mass times force, isn't it?
Yeah, and what's force is
It'd be gravity, right? It's like 9.8.
Yeah. Now, in this case, now that we're not doing this off the top of our head, we're actually writing this into Grasshopper, we can type 9.8, right?
Yeah.
We can be more specific. And then we want this in kilonewtons, so what's the last thing? Because at the moment, this is giving us newtons. So what's the last thing we want to do?
Do you divide by 1,000?
Yep, that's it. So, we're looking at 14.93 kilonewtons. Does anyone want to dispute the maths that I just did, just in case? Nope. Okay, cool. So yeah, if we want to throw a cutter in here, we're gonna put 14.93 kilonewtons into this unit Z, and I know what I'm doing, anyone who's watching. So I've plugged it in. What do I get? What looks like it's wrong here?
It's not negative.
Right, exactly. So we can put that in any of this maths formula, and there we go. Now I'm going to set the deformation back to 100 because now we're actually getting into realistic display scales. Look at my utilization. It's still at 12%. It's still at 7. Like it's actually doing, not still's the wrong word. It's doing pretty good, right? 12% and 7% is a decent utilization with these structures. And you know, I can rack this up. I can make this like, how many cars can we pile on it in the center of this bridge? Let's stack them on. Okay, we've got 2 cars. 3, 4, 5, 6, 7, 8. Okay, so it's at this point here that we're starting to see the utilization getting pretty high, right? A number I really want you guys to remember when you're working with this is that it's 80%. We don't want these numbers basically going under negative 80% or over positive 80%. And in this case, this particular bridge is in more compression than it is in tension. And so it's roughly at this point that we're probably going to see a failure in this bridge, or at least a failure in some way. Like we've gone well over. So let's say we actually have to support the fact that there are 10 cars that need to be, smack bang in the center of this bridge. That's a reasonable amount of cars to fit on a 14-meter bridge, and we've actually stacked them all in the center. We're going well over 100%, so these guys have definitely snapped and broken. Right, that's what I'm seeing here. So what I can do is I can start playing with the parameters and actually start changing my design, knowing that I've got this weight that I need to deal with in the bridge. I can say, well, let's add some extra members to this. Is that going to help? Are those extra members going to assist? No. Look at that. What did that do? Did it make it better or worse? I had 10 and it was at 104. Yep. And now I have 12 or 6, and it's now 130. So what's that telling us? It's telling us that the steel is contributing just as much to that problem, the weight of the steel, and adding extra elements is not going to solve it. So what's likely is that we need to start playing with our profiles. That's our flange, right? Thickening them up. And in doing so, look, we've just brought that back under 80%. Okay? Now there are lots of different ways to solve these problems, okay? And we've sort of talked about a lot of them. The way that a structure is designed, for example, if the way the structure is actually drawn, its actual 3D form factor can also change. So, I can actually pre-camber this thing. How did I break it? How did I break this? I can pre-camber this thing. Why is this broken? Let's find out. What did I do wrong? Line like curves. Line like curves. Bending. That's got to be on. This is telling me I've got eigenmode problems. Let's just do this. That'll probably... No, that didn't solve it. Meh. Those are the endpoints. Well, can you see anything that I've done wrong? The only thing I did was change the line.
Yeah, not sure. I'm trying to see.
You know, now that's not working. This is probably not working now. This fickle program. I think I know what's wrong. Just be careful also, you know, most structures aren't actually two-dimensional. It might be that this is drawn askew and it... But why would it matter? Why would it matter now? Can you recalculate, please? This is the other thing. If this thing breaks, sometimes if you just can't work it out, save it. Remember. I'm just gonna save this guy as well. And we'll restart. This is the other thing. Don't feel like all is lost when these things don't work, because I have problems with Karumba. You know, sometimes it's just one tiny little bug somewhere in the system and it just won't work. So just try and create a support network with each other on Slack, which should help. Let's do this. Okay.
Yeah, why is it not working even when you use the original line?
I don't know. It's suddenly decided that it's too complicated. The thing is, it is working. Like, it is deforming. Maybe we can just ignore that error at the moment. Let's check that one. So it is working. It's just complaining that I think it's worried about the this thing sort of like pulling off off axis. It might be actually. It might be my divisions. Maybe not. No. Okay. Well, look. It does look like it's working. But you can see with it pre-cambered, it isn't. Oh, it's off. You can see with it pre-cambered. See that just that tiny little archway that I've set there. Just the like that's a slope that's generous enough for anyone to walk across. That slope is. Let's quickly make a weave. Oops. So we're getting 72% versus 55%, right? Like just that tiny little camber has meant that we've been able to increase the number of cars. You know, let's have 20. You know, it's allowed us to add 4 to 5 extra cars to that structure just with that tiny geometry change. So
Andrew,
yes, go on.
do you mind just going back to the equation for the cars? How you did that with the slider?
Sure. So
Just missed that.
what I did was I took the weight of the car in kilograms. Weight, I shouldn't say weight, the mass of the car. The formula that I've used is mass times acceleration divided by 1,000, and I've just made that 1,000 negative so that any weight is actually going to be pointing vertically down, and then I've times that number by 15. So I've said, okay, there's 15 cars versus two cars. There's going to be a whole different bunch of ways that you guys can work out like live loads here. One thing I also implore you to do is with your structures, don't forget that live loads can be, coming from different axes. It's not always just gravity. We have wind loads that can lift roofs up or push structures over. So if a car was to effectively crash into the side of this thing, then we can create a load for that as well. We just change the direction of it, so we throw in y. Now it's not really our job to work out whether or not these things are going to survive a crash, but what am I doing wrong?
I think you put into elements instead of loads.
Oops. Okay, and then that thing's like completely smashed that out. It just can't handle it. Let's put it.
What's the point that you got the load being put on?
The point that the load is on will be this one.
Okay.
Or actually, it's maybe one of these two. If I lift that up and move it along, it'll move that to where it needs to go. I'm just going to turn off that extra load.
Mm-hmm.
You can see the forces if you turn your model view on. The force will show up. See that red line?
Yeah.
That's showing you which node that particular force is being applied to. So if I move that along or down, see now that force is on that bottom node there.
Mm-hmm.
Yeah?
Yep.
Okay. So we've got 30 minutes. What I'd like you to do is have a go at trying to have a go at starting drawing either your bridge or your cantilever using Karumba at the same time. you're more than welcome to just draw this thing up in Rhino to begin with, and then have it plug into Karumba. But eventually, for assignment 2, the thing that we want to be seeing is that there is some kind of like recognition of the patterns that were happening in your bridge or your actually. So you can draw your bridge, or you can draw potentially a new bridge that you're going to build. Either or, I just need to see you guys actually just playing with Karumba a little bit more than just what we've done just now. Have a go at it and just throw questions at me and Will for the next 28 minutes. Because this is even though you guys have gone through the gauntlet of 1150 and 1240, I think this is probably the most complicated script environment that you've been taught, because it's so fickle. So just have a go at it,
When is the first assignment due?
It's due this Friday at midnight.
And that's just the 2-page report
Yep.
on the bridge,
Yep.
past the bridge and the balsa bridge.
Yep. Assignment 2, I want you to pick one of those two bridges, one of those two structures. I need you to build a Grasshopper script that represents that particular structure, and then I would like you to improve the structure. Now that might mean completely eradicating all your ideas and starting from scratch. But I want to see, the reason why I want to see it in Grasshopper is you're going to put it into Karumba. And what we should be able to do is we should be able to take the analysis that you've done in assignment 1 and compare that with the analysis that Karumba is telling you in this assignment. And I want you to do this too. What did I get right and what did I get wrong?
Right, okay.
And then use this tool to infer a better solution and then see that solution through.
Mm-hmm.
Okay?
Andrew, can I just ask on that?
Yeah, go on.
My one bridge only broke because it fell and it was not built evenly.
That's fine.
So if I analyze it because I said that it broke mid-4, feels like a lot of tension on some of the joints. I'm not going to be able to do that in Karumba, am I?
That's fine. Look, just build your bridge in Karumba, like build it in Grasshopper, chuck it into Karumba, and Karumba is going to tell you some things about it, right? And very similar to what I did today, you can play around with all these different variables. There are just obviously going to be variables that you can't play with. So, for example, you can't change the strength of your balsa, or you can't necessarily make it extremely thick or extremely wide. Like, there are going to be limitations to what you can do. But even considering like what, geometrically, what can you do? Can you change whether or not something was a pin joint or a rigid joint, etc.? Then you can start creating the design for a better bridge or a better cantilever, and then building that cantilever or bridge. And seeing a physical change, like the critical thing here is that we've done something in reality. We're going into the digital world. Everything's abstracted, but we can use the digital world, this digital environment and model to make better decisions, and also learning about this stuff that we've done in the lectures and in class, and then going back and making an improvement. And that improvement is an improvement in reality.
I have another couple questions, Andrew.
Go for it.
First of all, where do we find the recorded lectures?
I've been posting them on Slack. They're also, I've been putting them up on YouTube.
Slack and a YouTube channel.
Yeah. I haven't uploaded last week's though, so I will do that.
One moment. I just want to load into Slack and see if I can find it, because last time I looked, I couldn't find it.
Go for it. I'll open Slack up at the same time.
So all I know what to do is to go into code 2121 where would the videos actually? Oh, the YouTube. Okay,
You got it?
so yeah. Okay, all right. That was a lot simpler than I thought it'd be.
So look, I'll post in there. Also, a few people asked me directly previously, and so I've posted things to them directly. But the idea is that they'll go and slate. It's the easiest for me, you know. Like I'll set this thing to upload at home, and then I might go out, and then it'll tell me that it's finished processing, and then I'll just get the link and throw it on my phone through Slack. So that that's the first place you can find it. Or subscribe and hit the like button on those videos, and you'll get told when they get uploaded.
Another thing was, is it okay to the course outline that's on Moodle?
Yeah.
I know it seems like it's for like a different time period, like it's for March or something.
You want me to go change it now? Because
No, it's fine. It's just, is it okay just to read for like the assignments and stuff? Like the descriptions there would be accurate.
They are. The only thing I've changed is I've shifted. You guys, there was a requirement in the first assignment to write a Grasshopper script, right, in the course outline.
Yeah.
The reason I've shifted that is that I haven't had enough time to teach you guys in class the Grasshopper side of things, and as well, I got a kind of sense from most of you that maybe that might have been a bit too difficult to ask of you, especially knowing your previous experience with Grasshopper. So that's why I've kind of, number one, I don't need you guys to write multiple Grasshopper scripts. I only need you to write one for either the bridge or the cantilever, so don't do two. And hence, I've just kind of relaxed that. So if anything, the course has become a little bit easier rather than more difficult.
And the Grasshopper script that we do write, we hand in assignment 2?
Yes. Yep.
Yeah.
Now, now this is another thing I want to talk to you guys. When would you like assignment 2 to be due? Because we have basically it's going to eat into assignment 3, and you kind of want as much time in assignment 3 as possible. But at the same time, assignment 2 is a really useful exercise in nutting out all the weird problems that you might need when you get into assignment 3. We've got this weird non-teaching week as well. Is it week 6 this term?
Yeah, something like that.
So this is week 4 this week. So next week is week 5, and the week after is week 6. After week 6, we technically have week 7, week 8, week 9, and week 10. So we have 4 weeks after that to actually do something. And the final week, week 10, or let's shift that to week 12, everyone gets a 2-week extension. That particular week is you presenting, so that's not really a useful week. So we've got 3 weeks to really talk about your final assignment. If we make this particular second assignment due either directly before or during or after week 6. So shall we? 3 weeks is not long, but we can do it. The thing is, I don't think it's fair on you guys to make this due next week either, right?
I would super love it if assignment 2 wasn't due next week.
Yeah, we're not going to make it due next week. So what we'll do is we'll say you've got all of that week off to do this assignment. I'm not going to make it due during that week off. If I make it due the Friday after week 7's class, is that going to be okay for everyone? Is that going to get in the way of anyone else's courses?
That'd be great.
That seems good to me.
Yeah?
Yeah,
Sounds not.
Yep, sounds good. Look, I'd rather err on, I prefer starting, like if we can start the third assignment, like as in teaching what needs to be done just before you submit the second one, that would be better for me timing wise. So is that good with everyone?
Yeah, that works.
Okay.
Works.
That's only 2 people. If anyone has a problem with that and doesn't want anyone else to know, just send me a message.
Was that Friday week 7? Friday week 7, yeah.
Yeah, it's the day after. It's the Friday after we have, like, because it's not like I need it to be due on the Wednesday, right?
Right. Okay.
I'm not going to mark it on Wednesday. All good?
Yep. Oh,
Yep.
Deal.
Sounds good.
Okay. Now, please go write some Grasshopper. Go.
Is it better to focus on the 2D aspect of the bridge, or
You should look this right now. I've been focusing on this thing as if it were 2D, like as if it was a flat plane. But trust me, there's no structure in the world that's going to work well in just 2D. So definitely think about 3D. You guys remember my cantilever? I had to really make sure that cantilever, the weight on the end was balanced, or otherwise that whole thing was just going to twist and torsion out of control. And that's generally what would happen if I actually tried to run a car over this bridge. The world isn't perfect. The weight is going to be set to one side of this thing, and it's going to twist and fail. Okay, so I've just been doing this in 2D because it's easy, but you guys should really focus on trying to add some 3D-ness to this thing. 3D meaning, actually looking more like I'm gonna pull some Grasshopper magic.
cast a spell.
I'm gonna cast a spell. Yeah. Did I cast a spell? It looks like I did.
Oops.
And then Will,
Yes.
we can play tabletop role playing games soon.
Oh, that'd be good. Get your extra supports in yet? I think that's what we're missing.
Yeah, that's what I'm doing. My supports. That's a support. And then let's just duplicate the loads.
One side's the one side's not connecting.
What? No, they're connecting. There's just one side's not.
One side is falling down, another is not. Yeah.
Yeah. There we go. Now there's double the amount of cars.
Oops.
But like that's a far more realistic structure to be like, and you can see there's barely any force running across the horizontals, but that's because it's still sort of using that crappy unrealistic thing. Like, we're probably better off, if you really want to make this thing super realistic, which is not absolutely necessary, then you can reconstruct this unit Z, actually put some forces in other directions, etc., and then we should start seeing and minus 5. No, you can barely see it. It's because there's barely any force there. But yeah, there's. You can see that deforming, like a bit weirdly now. If that you can see it sort of like skewing off. There's some torsional elements. So try and sort of add some random forces in different directions just to represent the randomness of the real world. Also, scale your model up. So if your model was this big, so it was 30 centimeters long, then maybe think about that as your members were 30 centimeters long, then maybe think of that as like a 5 meter or 3 meter member length in reality. Because Karumba's not going to tell you how to make a miniature bridge. It's only going to tell you how to make kind of like a realistically sized bridge.
So the combo is designed for like the actual instrument.
Yeah, it's not designed for making miniature models. No.
So I can't use it for designing my wing.
Your wing.
my monoplane's wing structure.
You could look. You can always scale this stuff up. The problem is that it is designed by a structural engineering firm that do structural engineering on architecturally sized buildings from pavilions to airports. It's there. Look, maybe if you make friends with some of the industrial designers in the class, they can point you to. Well, you're using SolidWorks, right?
Yeah, the SolidWorks takes so much calculation power.
Well, then yes, I'd say yes. This can do the calculation for you. You just need to do the scale. You need to scale it up a little bit. You need to make sure that everything's scaled properly. Because this is quite a light
version. Version.
So it doesn't want to do the full like solid deformation. It's doing finite element analysis. It's reducing quite a lot of the computation out. So
I just saw
Jack,
it just like that. Finish calculation for like 3 seconds.
There's only one way to find out, Jack, and that is if you give it a go.
Yep, I'll try.
Yep.
Oops.
Cool.
Damn.
Andrew, I got a question.
Yeah.
So regarding the bridge in Columba and making it bigger, so as in scaling up, what about the material? Do we still use pasta as the material, or do we change it to something else?
Look, you've got a bit of time now to go get some balsa. Just go get some balsa
for the bridge.
Yeah.
Yep.
Look, there's an obvious change in that you're using balsa instead of pasta compared to the previous one, but look, you're going to see significant improvements in the structure, unless maybe you're like Martin, who just made like a perfect truss, and is personal best. Let's see if Martin can do even better if he's using Karumba.
Yep, got it.
Andrew.
Yeah.
When we installed it, you asked us to do full instead of trial version.
No,
right?
No, I didn't.
No.
Other way around.
Yeah.
Okay.
You need to uninstall it
because I'm getting maximum number of beam elements.
You need to uninstall it. We want the free one, not the full one. Free one. No worries. Cool.
Is this Grasshopper script going to save if I uninstalled it and bring it back in?
Yeah, it'll work. Yep, it should work. You haven't used any restrictive components yet. So there's a whole bunch of, if you're actually interested in this stuff long term, there's a whole bunch of algorithms that aren't showing up, which do like genetic algorithm based solvers to actually work out how thick the members need to be, rather than you having to solve that. So there's some really clever things, and Sasha Bodenberger from Bollinger Grauman. I've got to practice my German. He usually was the person who would come and do like a free workshop on this. And part of that workshop, that workshop would go a lot longer than 2 hours, though. But you know, he actually talks through a lot of the structures that Caramba has been involved in. So all of these, like on their website, so like this CIAB Pavilion was a design. It's just a bunch of hyperbolic paraboloids. You guys remember those, right? But they're made in steel rebar that's all welded together. And Caramba was used. It's actually used. It's not rebar. It's but steel rods that are bent into shape. It's used to actually solve where the forces are traveling within those shells, and so these forces are then used. Like if you actually know the direction forces, then you can actually build a lighter structure by knowing where they are, by putting the elements resisting those forces in the direction that those forces are traveling, which means that those elements are only ever really, you know, getting affected in compression or tension. So these really, really thin, like.
Wait.
Hello?
Is that it? Well, is this one? Is that the one in front of the bird nest?
Yeah. Yep.
Oh, okay. I've been to there. All right. Sounds familiar.
Yeah, you can look. You just you know, based on the scale. You see these guys standing on it. They're basically standing on like bamboo, thin, steel sections, which is not normally a scale of steel that you would see in a structure like this. It would be a lot thicker if it was just steel holding this thing up. So the thing is, if you can optimize the steel and weight of your profile, what you're actually doing holistically within your building is you're actually reducing the weight of that particular object on the whole building. So, like, if we look at, they've actually got an interesting example. Maybe not. If we look at a wall, here we go. This is cool. So this is what a typical concrete wall might look like. It's actually being used as a shear wall, and it's got a universal UDL or a line load applied to the top. And Caramba, in its most expensive and complicated form, is able to tell us where the primary force diagram and force direction travels through that wall. And so with this wall in bending, you see this element here, these elements in compression, and the blue elements in tension. And so you could actually design this concrete wall. Normally we would fill that concrete wall with just a simple grid of rebar, and the rebar would be excessive. If anything, the rebar, basically what we're saying is the rebar in that concrete wall, rebar being steel, right? Just to double check with you guys. The rebar in this section and in this section and in this section would be wasted. It's effectively just there because we're doing brute force structural support there. Whilst the rebar effectively allows the concrete wall to be able to deal with tension. So all of these elements that are in tension, that's where the rebar is actually being formed. So if you can somehow build this wall, and it's an expensive process, but if you could build this wall where there are steel cables running in the blue direction, everywhere there's a blue line, there's steel cables running through there, and you leave all the red zones as just solid concrete, we can actually reduce the dimensions of this wall and the weight of this wall in our building, and therefore everything else in the building can actually reduce because we are supporting less weight in that particular area. So the more we can shave off everywhere, the better. And we can talk about cost and all of that, but it really comes down to also sustainability. If you can make a more structurally efficient building, you are making a more sustainable building. And buildings are significant contributors to where we stand with our sustainability targets everywhere in the world. And so if we can somehow reduce the amount of energy that they use, and so therefore, reducing the amount of steel and concrete that goes into them, then we hopefully will have a better future, especially because there are going to be a lot more buildings getting built in the near future. So there's a little ethical dilemma to add to the end of this, and as to why are we trying to make these buildings better? It's sustainability. Cool, guys. I'm going to quickly go grab lunch. I know this is super weird that I mention this every time, but Tim, can we have a chat tomorrow rather than today?
Yes.
Good. Thank you.
What time? Same time?
Yeah, around the same time. It's fine.
All right, cool.
Let's talk on Slack just to double check. But
yep.
Thanks, guys. I will see you next week. I am looking forward to seeing the assignments appearing in Moodle. I have not set up the Moodle thing, but it will be set up today. I will make sure that you're getting paid. And we're good.
Oh my.
Awesome. Thanks so much for today.
Yeah, thanks. I better go try to take care of my cat.